In this video, we move from understanding hypothesis testing to actually carrying it out. The focus is on calculating test statistics using both Z and T distributions, and performing full hypothesis tests for population proportions and population means. The goal is not to memorize formulas. The goal is to understand how to choose the correct test, what information the software requires, what conditions must be checked before trusting the results, how the test statistic connects to the p-value, and how to interpret the results correctly in context. Every hypothesis test follows the same structure. We begin with a claim about a population. Before looking at the data, we write the null and alternative hypotheses. We choose a significance level before running the test. We collect a sample and compute a sample statistic. The software then calculates a test statistic. That test statistic is used to calculate a p-value. Finally, we compare the p-value to the significance level and write a conclusion in context. No matter which test we use, this structure does not change. The first step is choosing the correct type of test. Ask what kind of variable you are working with. If the data represent yes or no outcomes, such as success or failure, satisfied or not satisfied, then you are testing a population proportion. Proportion tests use the Z distribution. If the data represent measured values such as time, weight, height, cost, or scores, then you are testing a population mean. Once you know it is a mean test, ask whether the population standard deviation is known. If the population standard deviation is given, use a Z-test for the mean. If the population standard deviation is not given, which is most common, use a T-test for the mean. A simple rule to remember is this. Yes or no data lead to a proportion test with a Z statistic. Measured data lead to a mean test. For mean tests, known population standard deviation leads to Z. Unknown population standard deviation leads to T. The only difference between Z and T for means is whether variability is known exactly or estimated from the sample. A test statistic is a standardized measure of how far the sample statistic is from the value stated in the null hypothesis. It expresses the difference between what we observed and what was claimed in units of standard error. A positive test statistic means the sample value is above the null value. A negative test statistic means it is below the null value. The magnitude of the test statistic tells us how large the difference is relative to expected sampling variation. A very large positive or negative test statistic means the sample result is far from what the null hypothesis predicted. A value close to 0 means the sample result is close to the null value. The test statistic is then used to calculate the p-value. Larger absolute test statistics generally produce smaller p-values. The p-value represents the probability of observing a test statistic at least as extreme as the one calculated. Assuming the null hypothesis is true, it measures how surprising the data would be if the null hypothesis were correct. The decision rule is always the same. If the p-value is less than or equal to the significance level, reject the null hypothesis. If the p-value is greater than the significance level, fail to reject the null hypothesis. Let us begin with hypothesis tests for population proportions. These tests are used when the data are categorical and each observation is a yes or no outcome. Before performing a proportion test, check conditions. The sample should be randomly selected or reasonably representative. Use the null proportion to calculate the expected number of successes and expected number of failures. Both expected counts should be at least 10. These expected values are based on the null proportion, not the sample proportion. If these conditions are not satisfied, the p-value may not be reliable. To perform a proportion test using software, you must enter the null proportion from the null hypothesis. You must provide the sample size and either the number of successes or the sample proportion. You must choose the direction of the alternative hypothesis. The direction matters because it determines how the p-value is calculated. Choosing the wrong direction changes the p-value and can change the final decision. You must also specify the significance level. Consider a two-sided proportion test. A company claims that 60% of customers are satisfied. A sample of 100 customers is taken, and 55 report satisfaction. The null hypothesis states that the population proportion equals 0.6. The alternative hypothesis states that the population proportion is not equal to 0.6. In the software, enter the null proportion as 0.6, the sample size as 100, and the number of successes as 55. Select a two-sided alternative, and choose a significance level of 0.05. Suppose the software reports a z-test statistic of -1, and a p-value of 0.32. Because 0.32 is greater than 0.05, we fail to reject the null hypothesis. We conclude that there is insufficient evidence that the true proportion of satisfied customers differs from 60%. The wording differs from matches the two-sided alternative. Now consider a left-tailed proportion test. Suppose a manager believes satisfaction has dropped below 60%. The null hypothesis states that the population proportion equals 0.6. The alternative hypothesis states that the population proportion is less than 0.6. Using the same sample values, select a left-tailed alternative and the same significance level. Suppose the software reports a p-value of 0.04. Because 0.04 is less than 0.05, we reject the null hypothesis. We conclude that there is sufficient evidence that the true satisfaction rate is less than 60%. Now consider a right-tailed proportion test. Suppose the manager believes satisfaction is higher than 60%. The null hypothesis states that the population proportion equals 0.6. The alternative hypothesis states that the population proportion is greater than 0.6. Using the same sample values, select a right-tailed alternative. Suppose the software reports a p-value of 0.96. Because 0.96 is greater than 0.05, we fail to reject the null hypothesis. We conclude that there is insufficient evidence that the true satisfaction rate is greater than 60%. The wording greater than matches the direction of the alternative hypothesis. Now let us move to hypothesis tests for population means. These tests are used when the data are quantitative. Before performing a mean test, check conditions. The sample should be randomly selected or representative. If the sample size is small, the data should not show strong skewness or extreme outliers. If the sample size is large, the central limit theorem allows the sampling distribution of the mean to be approximately normal even if the data are somewhat skewed. First, consider a mean test where the population standard deviation is known. Suppose a manufacturer claims that the average lifetime of a light bulb is 1,000 hours, and the population standard deviation is 100 hours. A sample of 40 bulbs has a mean lifetime of 970 hours. The null hypothesis states that the population mean equals 1,000 hours. The alternative hypothesis states that the population mean is less than 1,000 hours. In the software, enter the null mean, the population standard deviation, the sample mean, the sample size, select a left-tailed test, and choose a significance level of 0.05. Suppose the software reports a z-test statistic of -1.9, an a p-value of 0.03. Because 0.03 is less than 0.05, we reject the null hypothesis. We conclude that there is sufficient evidence that the true average lifetime is less than 1,000 hours. Now consider a right-tailed z-test for the mean. Suppose the alternative hypothesis states that the population mean is greater than 1,000 hours, and the software reports a p-value of 0.97. Because 0.97 is greater than 0.05, we fail to reject the null hypothesis. We conclude that there is insufficient evidence that the true average lifetime is greater than 1,000 hours. Now consider a mean test where the population standard deviation is not known. Suppose a teacher claims that the average exam score is 75 points. A sample of 20 students has a mean of 72 points, and a sample standard deviation of 8 points. The null hypothesis states that the population mean equals 75. The alternative hypothesis states that the population mean is not equal to 75. In the software, enter the null mean, the sample standard deviation, the sample size, select a two-sided alternative, and choose a significance level. The software calculates a t-test statistic using the t-distribution with degrees of freedom based on the sample size. The t-distribution is wider than the z-distribution for small samples because it accounts for additional uncertainty when the population standard deviation is estimated rather than known. As the sample size increases, the t-distribution becomes closer to the z-distribution. Suppose the software reports a t-test statistic of -1.6 and a p-value of 0.12. Because 0.12 is greater than 0.05, we fail to reject the null hypothesis. We conclude that there is insufficient evidence that the true average exam score differs from 75. When data are entered into software as raw values instead of summary statistics, the program calculates the sample mean, sample standard deviation, and sample size automatically. The required inputs and interpretation remain the same. You still provide the null value, select the direction of the alternative, choose a significance level, and interpret the p-value in the same way. The software output typically displays the test statistic, the p-value, and for t-tests, the degrees of freedom. You are responsible for reporting the null and alternative hypotheses, the significance level, the test statistic, the p-value, the decision, and a conclusion written clearly in context. Common mistakes include selecting the wrong direction for the alternative hypothesis, failing to check conditions before running the test, writing hypotheses using sample statistics instead of population parameters, saying that you accept the null hypothesis, or failing to match the wording of the conclusion to the direction of the alternative hypothesis. To summarize, choose a proportion test with a z-statistic when the data are yes or no. Choose a mean test when the data are quantitative. Use a z-test for the mean when the population standard deviation is known. Use a t-test for the mean when it is unknown. Check conditions before trusting the output. Enter inputs carefully. Interpret the test statistic and p-value together. Compare the p-value to the significance level. Write a clear conclusion that reflects the direction of the alternative hypothesis and refers to the population. The distribution may change, but the logical structure of hypothesis testing always remains the same, and every conclusion is made under uncertainty.